welcome back. Hopefully everybody had a nice break and snack. It's a second morning session. We're going to have a 30-minute talk, another 30-minute, and then 30 minutes for poster pops. It's 25 minutes plus 5 for questions. Please save those questions till the end or post them in the chat. First talk will be by Courtney Dressing of Berkeley, an expert, well known for her work in exoplanet demographics, transits, and RVs, and she will be telling us about system architectures. Thank you.
Great. Thanks, Tim. It's wonderful to be here with all of you. Today, I'm going to talk about architectures, and I thought it would be fun to start with a model of our own solar system shown here from the 1700s. I also want to point out, as we've heard many times already, that our knowledge is not yet complete. So here's a plot we've seen multiple times in one form or another, showing the search sensitivity for various techniques, as well as the planets in the solar system and the ones we've detected. And anyone in the room, perhaps even in the back row, can tell that the solar system planets and the exoplanet populations are pretty different on their locations on this plot. And that does not mean that we're totally weird, that no one else in the universe is like us. Really, it's a reflection that we're only scratching the surface of finding planets. I'm currently in the process of writing a review paper about the sample of planets in our neighborhood, those planets within 10 parsecs of the sun. And one of the plots I put together for that was this one here. So here what you see is the number of planets known to exist within 10 parsecs, plotted by discovery year. And I'm cheating a bit here. I'm not plotting the discoveries of planets that were later retracted. So this is the discovery year of all of the planets that are known today to exist within 10 parsecs. And what you see is that it's still going up. It has not leveled off. We're still learning about new planets very, very close to us. So if we don't even know our own neighborhood, how could we possibly claim that we know all of the planets in the galaxy, let alone the universe? So I want you to take this talk with a gigantic grain of salt, that we're talking about architectures, but we're only just barely beginning to understand architectures. It's like we're trying to understand the architecture of Los Angeles from inside a single room in someone's house. If you want another example of how we're still learning where the systems are, I encourage you to check out this poster by Caleb Hirata. And disclosure, Caleb is a grad student working with me, so I'm a little biased here, but I did my best to highlight all the posters that are related to architectures, and I want to encourage you all to talk to each other about the exciting work you're doing. This is a very new area in exoplanet research, and it's something where I think there are a lot of key discoveries waiting to be made. Let's start with some definitions. So in my family, oh, thanks, Tracy. All right, so in my family, one of us is an architect, and it's not me, it's my sister. So with apologies to her, I wanted to start off by defining systems and architecture. So first off, what is a planetary system? If you close your eyes and imagine a planetary system, you might, just because of where we live, think of a single star with planets. But that's only one example. Really, we could have multiple stars with planets. We could have a brown dwarf with planets. We could have planets on their own without a star. The only thing we need is we need a gravitationally bound group of objects that includes at least one planet, and then we have a planetary system. If you want to get really science fiction, maybe you have a massive spacecraft and a planet. You could call that a planetary system, but we'll save that for the sci-fi novels. An extreme example are planets orbiting black holes, and there's a poster about that. If we have an isolated single planet, that's not a system because it's just one object, although there would be perhaps a system of things on the planet like geology. But in this context, we're not going to treat single free-floating planets as planetary systems. But there's another paper showing that those single free-floating planets can affect planetary systems. So everything is connected. And also, those free-floating planets were probably ejected from a planetary system. So they were either part of a system in the past or might be in the future or are currently a part of a system in the case of those that are bound to other objects. I also mentioned that we could have multiple host stars. I wanted to have a whole section about what we know about populations of planets orbiting binary stars, discussing planets orbiting one star or both stars and similarities between those planets and what distances from the star planets are likely to exist. What we see is that very close to a system where if we have two stars, if you have the case where a planet orbits both stars, typically that planet will have a much longer orbital period and the binary will have a shorter orbital period. So for the planet, it's almost like it's just orbiting a single star. That would be a circumbinary planet because the planet goes around the binary. The other case is a circumstellar planet where you have a binary system and there's a planet orbiting one of the stars, or maybe both stars have planets, but they're orbiting just a single star. In that case, what you see is that the planets tend to have pretty short orbital periods relative to the period of the stellar binary. Where things get unstable is when the planet period and the star period start to become more similar, and you could imagine that you would have more dynamical interactions in that case. For much more about this and how you can find planets with the radial velocity method, check out this poster. And if you want to think about which star actually hosts the planet, this can be trickier than you might expect. And it's important because we determine planet sizes and masses relative to that of the host star. So if you have a system where there's an F star and an M star, and you think the planet orbits the F star, but it actually orbits the M star, you're going to get everything wrong. So we need to, for our demographic calculations, account for the likelihood that maybe the planet actually orbits the smaller, less massive star. Okay, I promised you definitions. What is architecture? There are many definitions in the dictionary. Most of them have absolutely nothing to do with what we're discussing today. So this is a little bit of abusive terminology, but I was delighted to see that the note for definition 2 mentions that it can also be specifically relating to designing and building structures that are habitable. So that's connected to astronomy. And then if you look further down, method 6 here is a method or style of building. So if we imagine that we're building a planetary system, perhaps that definition is pretty related to astronomy. So what is a planetary system architecture? We said planetary system is a gravitationally bound group of objects, including at least one planet. Architecture is how it all fits together. So if we want to describe these planetary system architectures, what might we put on our postcard advertising the properties of the system? Well, I'd like to know how many objects are in the system. What are they? We can go back to Monday's discussion about what is a planet to figure out how many numbers we put in various categories. We also want to know, how are these objects spaced? Are their orbits similar? Do they have a wide range of inclinations? Are they on circular orbits? Are they on highly inclined orbits? Do those planets interact with each other? Do we have binary planets in the system? And if we look at the various objects in the system, how similar are they to each other? And then on a meta level, if we were to take a variety of planetary systems, how similar are those different systems to each other? For these comparisons, if we're comparing planets within the single system, that would be intra-system similarity. And for planets between systems, that's inter-system similarity. There are many, many ways to classify systems. Some of them are on the posters out there. So here's one example by Alex Howe. Here's another by Plakolba. And if we look in the literature, Mishra et al. In 2024 proposed that we look at a metric, for instance, mass, and then we record in the system, how does that property change with increasing distance from the star? So in this example here, if you have a system where planets are indicated by these various dots here, if the number of planets is such that, if the planet mass increases as you go away from the star, we would denote that system as ordered. If the mass decreases, we'd say that it's anti-ordered. If the mass is roughly the same, we'd say that it's similar. And if it just seems to go all over the place, like it does in this green line, then we would say it was a mixed system. And you could do this for a variety of parameters, not just mass. So you could also do this with radius or perhaps density. And then you could compare the properties of real systems to the properties of planets produced by various planet formation models. And we heard about those earlier in the week as well. And then if you compare the distributions of parameters for the planets in the models to the planets in the observed sample, you get plots like the one on the right here, where here we're showing the likelihood that things are similar in the planetary system as we go from close to the star to further out as a function of the total mass of the system. You can see there's a cluster of blue points. Those look very close together, and that's because those are the systems that are similar. Then we have points up in the upper right. Those are red. Those ones are places where planets get larger, get more massive as we go away from the star. And then we also have the green case where there's a bit of variation, but they're drawn from perhaps the same distribution as the planets in the other systems. It's just a question of how you order the planets in the system. Okay, so that's one classification metric. If we want to get a closer look at that, we could also make plots like this one here. And you'll see a lot of plots like this in the literature. The challenge we have now is that there are so many multi-planet systems, it's actually quite difficult to make these so that you can fit them on a single slide. This used not to be a problem. But what we have is on the y-axis at the top here, or x-axis on the top, we have the name of the system. And then along the side, we're showing how far the planet is from the star. So very close to the star is at the top, far away is at the bottom. The circles indicate the sizes of the planets, and then the colors indicate how similar the masses of those planets are to each other. So if you have a system where they're all in a certain color, we would find, if we look on the left side here, these planets seem to be, the coefficient of similarity is this axis here. The color is the equilibrium temperature. That makes a lot more sense. So if you have planets that are the same size, they have high similarity in mass, and therefore they're plotted on the extreme left side here. And then as we go to the right, we see more disparity in the masses amongst the planets. So using this metric, you can then classify the systems as, is the mass roughly evenly divided amongst the planets, or is there one bossy planet that got all the mass and didn't let its siblings eat while they were growing up? The really fun thing comes when you take the observations of how the planet masses are distributed and you compare that to models where you form planets from planetesimals, you watch them behave, you watch them accrete material, and then you compare how does the mass distribution of those simulated planets compare to the real observations. And in this paper here, what Mishra et al. Did is that they fed planets in a variety of configurations. They varied the disk gas mass, they varied the solid mass from the disk, the metallicity of the star, and then they saw that certain types of planetary mass distributions tended to result from different configurations. So if you have a disk where you have a lot of solids, if you have many solids, you're more likely to end up with a situation where some planets are a lot more massive than others. But if your disk has less solid material, you're more likely to get a case where the planets have roughly the same mass. If you have a metal-rich host star, then you're more likely to get one of the trends where either the mass continues increasing with distance or decreases with distance. In the real world, we haven't yet found those decreasing with distance systems, but simulations suggest that they could exist. If you think about it, though, they would be much harder to detect with our instrumentation. So even if they do exist, we shouldn't have found many at this point. We'll learn more as we get increasing data from Gaia and Roman and radio velocity surveys. If we have a star with intermediate metallicity, not too low, not too high, that's when the systems are more likely to have a mixed configuration where the planet mass alternatively increases or decreases throughout the system. As the mass of the system increases, you're more likely to have dynamical interactions between planets, which then leads to all of the architectures except for the similar architecture. So this is consistent with previous work, trends such as the likelihood of having a gas giant planet increasing with stellar metallicity. There are many, many classifications. We could spend the entire time talking about different ways to describe systems. But for the rest of the talk, I wanted to use a framework presented in 2020 by Gilbert and Faberkey. This system was inspired by information theory. And one of the things I like about it is that rather than just comparing pairs of adjacent planets, it looks at the whole planetary system. So it gets a little bit more of a comprehensive view. They came up with 7 key metrics, and we'll walk through them. So the first one is dynamical mass. Essentially, this is if you take the mass of the system, and you add up all of the mass in planets and divide that by the mass of the star, how much of the mass is in planets relative to the star. Most of the time, there is very little mass in planets compared to the star. That is the case for our solar system as well. The next metric is how much variation is there in the masses of those individual planets. If you took all of the planetary mass, if you have 100 Earth masses and 10 planets, are all of those planets 10 Earth masses? Or is one planet 90 Earth masses and the remainder sharing the leftover 10 Earth masses? And here, these planets are organized such that on the left side, we have systems where there's at least one planet that's more massive than 100 Jupiter masses. And then on the right, all of the planets are less than 30 Earth masses. Sorry, 100 Earth masses, not Jupiter masses. We're talking planets, not stars. And as we go from the right to the left, the total mass in the system increases. If you focus on the right side of the diagram, where there are these smaller circles for less massive objects, you might notice that the circles seem very similar in size, and that means that they have similar masses. On the left side, though, we have a lot of variation. We have big circles and little circles, so there's more diversity in how the mass is divided. The formula for how you measure this effect, rather than just doing it by eye, is you compare the masses of all of the planets, you figure out how many planets are in the system, and then you ask the question, to what extent does the mass of any individual planet vary from the average planet mass? And then if you perform this calculation for the small planet case, and you compare what is the dispersion measured in real systems, you get this point on the left side, this vertical line that almost looks like it's the x=0 axis, because it's a very low dispersion. These planets have very similar masses. And if you were to just do random realizations, pulling these planets in any order, assigning them to stars at random, you would see a much higher dispersion. So we see that planets in systems with planets that are less massive than 30 Earth masses tend to be more similar in mass than one might naively expect. For the more massive systems, things are different. There, the actual system dispersion is marked by this black line, which is much closer to the middle of the random distribution. So we get a lot more diversity in mass as the total mass of the system increases. Okay, metric 3 is monotonicity. To what extent does the size of the planets vary in a uniform fashion as we increase the distance from the star? So we have 3 ways that we could describe a system. We could have a positive monotonicity, where the planets get larger with increasing distance. We could have a near zero monotonicity, where there's no clear trend towards increasing or decreasing planet size. Or we could have a decreasing monotonicity, where things get smaller with increasing distance. There have been a lot of studies discussing how planet size varies with distance. And what we find is that in this particular study with Gilbert and Fabrici, they couldn't say one way or the other whether there is a strong trend towards increasing or decreasing planet size with separation. But there are other studies as well, one by someone in the very, very back of the room a long time ago. And in that study, David Chardy found that in systems with at least 2 planets, where one of those planets was Neptune-sized or larger, more often than not, the larger planet was exterior to the inner planet. You might say, wait, that's only detection bias. You can't find a small planet further out. But it's not. Even after you correct for that bias, it's still true that the larger planet tends to be farther from the star. And this has borne out with more recent research as well. You might be confused, though, because we've heard a lot about peas in a pod. And I think it's important to point out that peas in a pod is not a universal phenomenon for all multi-planet systems. It's specifically for compact multis, where there are many planets close to the star. So if we put up a system of compact multis, this figure is from Weiss et al. 2018, and you can see what I mean about the number of systems getting so large that it's hard to put a graphic that you can all see the planets on. But what if you take those planetary systems and then you make a plot where you measure the radius of one planet and you plot it on the x-axis, and then you plot the radius of the next adjacent planet on the y-axis. If the 2 planets were exactly the same size, they would all line up along this 1-to-1 line here. They don't. There's definitely some scatter here, but there's a lot less scatter than one might expect from just drawing planets at random. So this is evidence that there is a correlation between the sizes of adjacent planets in multi-planet systems that are compact. If you look at the spacing between the planets, another finding from this work is that as you increase the total number of planets, the spacing between the planets tends to get smaller if those planets are small. And if you were to make the spacing between the planets really, really big, that system would stand out and appear to have a missing planet. And maybe that's because we haven't detected that planet. If you have a system with 3 or more planets, Weiss et al. Also found that the ratio of orbital periods between one neighboring pair of planets and that between other neighboring pairs of planets are correlated. So there's some self-similarity in how those planets are distributed. There's been additional work on this, some by Josh Wynn in the second row. And I love the title of this paper. This was the idea of split peas in a pod. So if you take your planetary system and rather than looking at all of the small planets as one uniform population, you instead divide them into two groups, the super Earths and the sub-Neptunes. What you find is that there's size similarity in each of those populations individually. So if you have a system with multiple sub-Neptunes, the sub-Neptunes have sizes that are correlated, and the super Earths have sizes that are correlated. There's less of a correlation between the sub-Neptunes and the super Earths, but if you compare their radii to each other and you plot the ratio of what is the radius of a typical sub-Neptune compared to a super Earth, you find that typically in a given system, these sub-Neptunes are about 1.7 times larger than the super Earths. It's pretty neat. Those were all for radius. You can also make this comparison with mass. In some papers, people do this by using mass-radius relationships. But I'm going to make a controversial statement and encourage you not to do that because those relationships are set based on what we've been able to measure. There's a lot of biases, and you can make a first guess. You can come up with a theory, but we're learning that planetary systems can surprise us. We have a decent sample of planets with masses, so let's use those. Let's not dilute that by adding in a prior expectation that planets behave a certain way and then concluding something that's based partially on things that we put in as input without proper evidence. So rant aside, if we plot the masses measured by radial velocities or transit timing variations, in this case, transit timing variations for a system, and we connect planets in the system. So here, each dot is an individual planet in a system. And on the left, these are real planets. On the right, this is a simulation. So for the real planets, if we have a system with two planets, we'll have one planet here, one planet there. We're plotting the mass and radius of one planet, the mass and radius of the other planet. You see that there's a correlation in both parameters. This might look a little scattered. It might not look like much. But if you do thousands of simulations where you draw values for these planets, you can get a random realization that looks like the one on the right. And if you compare the variations in mass and radius for the real systems versus the random realizations, you see that actually there's a lot less scatter in the real population than in the simulated populations. So not only are the P's similar in radius, they're similar in mass. Another fun thing to do with architecture is ask the question, okay, I found a certain planet. What's the likelihood that another type of planet also exists in this system? And now we're moving beyond the peas in a pod architecture. We're considering planets that are much farther from the star. So if we found a cold Jupiter, that actually is a really, really good sign that a system has a hot super Earth. Studies suggest that something like 90% of systems with a cold Jupiter have a hot super Earth. And about 7% of systems with cold Jupiters have hot Jupiters. That means if you found a cold Jupiter, there's a really good chance there's something else in that system close to the star. For more on this, check out the posters. There are actually multiple posters about this exciting topic. And the reason why we care about this is that we understand the distributions of planets within systems that can tell us more about where those planets formed and how they got to their current locations. Metric 4, and I realize I'm running out of time, so we'll go faster here. Metric 4 is how closely spaced are these planets. Many studies have shown that planets seem to be separated by about 20 Hill radii. But major caveat here, a lot of those studies inferred masses based on radii. This still holds, though, if you use planets where we've measured masses with radial velocity or transit timing variations. If we look at the period distribution, unfortunately, we've seen this plot earlier in the week. What you see is that there are some places where if you compare the period of an outer planet to the period of an inner planet, there are spikes in that ratio distribution. Those spikes occurred just wide of resonance, and that provides clues to how the planets got to their current formation locations. Those architectures are shaped by that migration, and the way the migration proceeds depends a little bit on the ratio of the planet masses. Metric 5 is gap complexity. So this is basically how predictable is the pattern of periods for the planets. What we find is that most systems have very predictable spacing. And for the ones that don't, the fact that there's a planet not there could be explained because we missed the planets. For more on that, see this poster. And also check out this paper by just graduated grad student, Emma Tertelbaum. And if I had more time, I would tell you all about Emma's research, but she's here, so you can ask her directly. Essentially, what she found is that if you use models to predict where planets should be, and then you look for those planets, many times they're not there, which means that we need to learn more about planetary system architectures, and that models that describe one class of planetary systems don't necessarily apply to all planetary systems. Okay, metric 6, how flat is a system? Do we have very coplanar systems or high mutual inclinations? Mostly, we have very flat systems. We have posters about that too. And then finally, multiplicity. This is the first question I asked. How many planets are in the system? This one's tricky because there's a trade-off between the inclination distribution and the number of planets. It looks like there's about 3 planets per system, but this is something that we're still working on. And with Roman and with microlensing, we're going to get much better at figuring out the total number of planets per system. And that number for 3 planets is within 400 days. So if you were to go further out in a system, you of course could pick up more planets. Right. We also see evidence that systems are truncated for the compact multis, that they could have more planets that should be detectable but are not detected. Are there things well beyond the edge of the compact multis? Do they have cold Jupiters further out? Time will tell. There's a lot of work we could do in the future. I didn't mention eccentricity much. We should definitely address that. It's a big question. We also should consider correlations between planet parameters, and we really need to do a better job with the multi-star systems. We can't just ignore them. Most stars are in multi-star systems. There are posters reminding us that planets orbit stars. We need to understand stars to understand planets. And I should say some planets orbit stars, not all. Cold Jupiters get eccentricities. And then to summarize, these are the metrics from Gilbert and Fabrici. And then these are the main conclusions related to those metrics. I also put a list of papers in if you want to learn more. Don't know if we have time for questions, but you can always find me at the conference. And thank you very much for listening.
I think we can squeeze 1 or 2 questions while the next speaker comes up. So if you have one you'd like to ask, please go ahead. All right. Oh, yes, go. One question.
Hello. Yeah. Thank you so much for the great talk. My question was related to while we are inferring these architecture of like the configuration of planets depending upon the size and all, how do we take into account the observational bias in the sense that like we were seeing like most of the planets were having the similar size in the mass, but that is it related to the observational sensitivity? Because if it is, it can find a system which has a particular mass, then if it has like similar masses of other planets, it would be able to find it. But it won't be the case if they are like mixed or has the variation in the masses.
Right. So the question is about how do we know that these trends we see are actually the underlying population rather than just a manifestation of detection biases. In these papers, I didn't discuss it here, many of the ways they do this is they simulate a population of planets that follows some underlying trend, and then they simulate observing those planets, or they simulate the detectability, and then they compare their mock observed sample to their true sample. So they're accounting for those selection biases. So when we say that there's a trend in planet size, we're acknowledging the fact that we were considering certain ranges of planet sizes, and we couldn't see planets below a certain size limit.
Thank you. Unfortunately, we need to move to keep to time. We have poster pops after this.